Okay, so our new unit for the next chunk of time, which we'll I'll have to kind of show you our calendar coming up. It looks like I went through my my calendar over break. What I was hoping to do is just make sure that it makes good sense, but I believe where we stand is that you guys will be having your next vacation. It's crazy we're already talking about the next vacation when we're on the first day back, but it's true. Good Friday is the 2nd of April, and so we're really not far away from March yet. So what happens is my plan is to have your test number 2. I did tell you this semester is a 3-unit, not a 4-unit, so there's less material than there was last semester. So currently my plan is to have your next exam on March 23rd, which is like 4 weeks from tomorrow, okay? So it's actually a much more limited amount of information. This is a topic that's known as analytic trigonometry. So I'm going to try to keep it a little bit short. That should put me in a perfect spot where you get no homework at all over that Easter break, that week plus, because I'm going to try to test you on the 23rd, even though the following week we're in class anyway. It'll keep us a little bit back from that, and I think that'll be a helpful thing for you guys. So anyway, just give you a little bit of an idea. So let's talk about this. So let's just say that we have this picture right here. Can you guys draw that picture for me? Just draw yourself a right triangle, and let's put a theta right there. Let's put an X. Now, again, this is not critical that I call this specifically X, but I did. I chose to do that because it's horizontal, and I made Y vertical. And what do you think that R stands for? Usually it's like radius or something like that, because a lot of times we think of circles when we deal with trig, although this is not unit circle. I'm not saying R has to be 1, although it could be. It's just something. Now, here's the deal. What do you guys know is the sum of all of the angles in any triangle, for that matter? They have to be 180. This part is already 90. So what is left? Has to be 90 degrees. Okay, so if I cover this up and you know that these two angles are a sum of 90, then what does this one right here have to be is 90 degrees minus theta, right? So if I told you this one was 6, this one would have to be 84. Are you guys okay with that? Or if I told you this was, 82, then this one would be 8. So what we tend to do, because of the fact that radians are just easier to play with, we tend to substitute instead of 90 degrees, what is that in radians? Pi over 2. So instead of 90 degrees, well, let's do pi over 2 minus theta. And remember, if we're in radians, we don't put any kind of extra stuff on it, right? Now check this out. Look at this top angle right here, everybody. Feast your eyes. What is the sine of pi over 2 minus theta? This angle right here is pi over 2. So what is its sine? Can you guys tell me what ratio that would be? The sine is what? Opposite over hypotenuse. So the sine of this thing would be x over r, right? Let's look at this angle. What is the cosine of theta? Plain old theta. X over r. So you see how the sine of this top angle is the same as the cosine of the bottom angle? So let's try this. What would be the cosine of pi over 2 minus theta? Can you tell me what is another way of saying the same thing? Well, the cosine of this top angle is y over r. What other ratio is also y over r? Look right here. What trig ratio would be y over r? The sine of theta. Now, do you notice anything that's kind of convenient there? The sine gives me a cosine, and the cosine gives me a sine. Hence the reason we call these the co. What does co stand for? Actually, it means, in this case, complementary, because what do these two add up to? 90 degrees. That's the definition from geometry of complementary angles. So these are my cofunctions. So anytime that somebody hands you something like this and you're like, dude, that's nasty, I don't like that, can you just substitute that in its place and make your life a little bit easier? In fact, that will be done in some of your homework assignments, okay? So any guesses out there what the tangent of pi over 2 minus theta? Hint, these are called the cofunction identities. Any guesses what would, if the sine went with the cosine, what do you think the tangent's going to go with? The cotangent. Any guesses what the cotangent is going to go with? The tangent. What do you know? How many of these identities are there? Well, it turns out there's 6 trig functions, so guess how many there are? There's 6 of them. So who do you think the secant is going to go with? The cosecant. Whee! No big deal. And the cosecant. Now, I have mixed emotions about this because is that a lot to memorize that you need to know all of those? Yeah, it is. But what happens every single time in every problem is you have this, don't you? Now, why? It's because this relationship right here, it's this, no matter what, if that's theta, that one has to be pi over 2 or 90 degrees minus theta. Those are called the cofunction identities. So in your homework, here's what they're going to do. They're going to say, if, this is a stupid example, but it's true. They'll say something like, if the sine of pi over 2 minus theta is negative 0.76, what's the cosine of theta? Well, look right up here. What does it say? It says this is the same as this. So what's the answer? You're done. Like, and my students always look at that like, it has to be harder than that, isn't it? It doesn't. It's that easy. What about if they said, if, here's number 2, if the secant of theta is equal to 2.75, what is the opposite of the cosecant of pi over 2 minus theta? Well, that is a little bit trickier because this thing is supposed to be the same as the cosecant right here. So what would that answer be? Because some jerk put a negative in front. It'd just be the same answer, but with a negative in front, no big deal. Okay? So if you see something that's kind of ugly, what am I giving you the ability to do? You can take anything that's ugly and what can you do with it? Make it prettier, right? Is that kind of cool? Simple little idea. So this is, again, this topic called analytic trig. Now, there's some building blocks. So in your textbook, what you'll see is they always have these green boxes. There's a green box with all of those. Where it comes from is that little picture right there. You guys cool with that? Not too hard. Second one. Sorry, blast from the past, odd and even. Now, as it turns out, when you look at these functions, every single one of them, all 6 will be even or they will be odd. So what you want to remember is even functions had y-axis symmetry. Odds had origin symmetry. Now, I am not going to choose to prove these to you. I'm just going to show you them visually. So I'm going to go ahead and drag a little Desmos over here to the side. And hopefully you can see this pretty quickly. I'm going to go ahead and reshare this with the online portion. Here we go. So let's say we have the sine of x. So here's the question. If f of x is this, what I told you is in an even function, I'm going to go ahead and make these go away. I was going to do something else with you, but I decided not to. But in an even function, f of negative x is f of x. So if when I replace f of x with a negative x, if I get the same thing back, it will be even. But if I do that, did I get the same thing back or did it rotate 180 degrees? See, this is kind of weird. The definition of an even function is putting a negative on the outside is the same as putting a negative on the inside. Are those the same? That matches the definition of odd. Now, here's the guess. If the sign is odd, who else do you think would automatically be odd based on its relationship to the sign? Almost. No, you were closer the first time. So check out the cosecant, everybody. What would happen if you put your finger right here at the origin and you spun it 180 degrees? So if you spun that 180 degrees, would you get the same thing back? So I'm going to do f of negative x, and here is negative f of x. Are those the same thing? Anybody have another guess? Let's see. Let's take a look at this dude right here, the cosine. What do you guys think? Is this even? If I spin it 180 degrees, do I get the same thing, or does it have symmetry across the y-axis? Symmetry on the y. Who else would go with that one? If the cosine has it, the secant's going to have it. Cool? So you're right. If the cosine has it, look what happens when I go ahead and I try f of negative x. It's the same exact thing. So when I try to replace the inside with a negative x, I got the original function back, no changes. I really should make this a different color so we can tell that we're getting something different, but notice they're the same no matter what I do. So the secant's going to go with this. How about the tangent? What do you guys think about the tangent? Is the tangent going to be even or is it going to be odd? Does this have origin symmetry or y-axis symmetry? So if I spin it, is this the same as it started out with? Totally different. But this says replace the inside with a negative. This says put a negative on the outside. One reflects across x, one reflects across y. Are these the same? You guys see it, how they're the same? So here's the landing the plane here is we have a set of relationships that are even and odd. And it turns out the sine is an odd function, as is the cosecant, as is the tangent, as is the cotangent. And the even functions are cosine and secant. So I've told you before, I don't like memorizing. You know what I memorize? I remember that the cosine and its buddy is even, everybody else is odd. That's just easy peasy. Now, here's how that relates to what we did last year. Because it literally was last year, early in the year. Remember, odd functions were ones where f of negative x was negative f of x. Even functions were that f of negative x is f of x. So when you guys were taking your last test, and I kid you not, this is what I did. When I asked you a question like this, some of you are like, oh, he was wanting me to rotate backwards. Sure. Or, since it's an odd function, it allows me to pull the negative in front and get the same answer. And this says, oh, just rotate forward, but then change the sign, and you should get the same answer. So this answer would say rotate backwards 7 pi over 6, where the sign is positive a half. This one actually says, let's rotate forward to the value negative 1/2, but then put a negative in front, and I get a positive. You see how you get the same answer either way? That totally happens. And so there was a specific question on your test that I was a little bit mean with you guys. And it was this one right here. And some of you guys looked at that double negative and went, ah! But if this is odd, what can I do with that negative? That negative on odd functions can pull in front. So if I pulled this out, what's going to happen to that negative in front? It's going to cancel. And so we could have just answered this one where it's root 2 over 2 and we're out. So there's some weird little games that you can play. Now, do you have to play those games? No, you don't. But sometimes it can be very, very helpful. Okay, so far, was this rule right here a critical rule? I would say absolutely not critical. Was even and odd a critical rule? I would again say not really. It sometimes saves us a moment or two. Here is the big one. So if you could put stars next to this in on your notes or in your brain or whatever the heck you put your stuff, this is pretty amazing stuff. And I can't stress enough how significant these things are. So we're going to have 3 new identities that are going to be really, really important for us. And so I'm going to go over 1 or 2, and then I'm going to ask you to try something for me. Okay. So just like what we did before, I'm going to put a theta right here. Let's put an x right here, a y right here, and what should I put right here? Just like what we did, let's just call this r, okay? Now, what do you guys know that the Pythagorean theorem tells us? Off of this triangle. Don't think trig, just think regular old Pythagorean theorem. What do you guys know to be true? What is x squared plus y squared? It is r squared. So I'm going to put this up here at the top. These are called the Pythagorean. Now, why do you think we would call it Pythagorean? Is because, notice I'm going to use the Pythagorean theorem over here. These are called Pythagorean theorem or Pythagorean identities. And these are super, super helpful, amazing little suckers, okay? But they're all based on the Pythagorean theorem. And so here's what I want to figure out. The idea is to take something that looks hard and replace it with something that's easy. You guys follow me? Every single one of these things, take something hard, make it look easy. Take something that might be a little bit hard and make it a little bit easier. So let's see if we can figure out something. So can you guys please just figure out what is the sine squared? So do the sine, but squared, okay? Can you guys try that? So who's got, what is the sine? From theta, what is the sine? Y over r. So if you squared that, what would you get? You'd get y squared over r squared, right? What is the cosine squared? Okay, so if that's true, remember we have fractions, so we'd like to add those fractions together, but to add fractions, you need a common denominator, right? What do we have? We have r squared. That's awesome. We have a common denominator, so I could put them together and say it's y squared plus x squared over r squared, can't we? By the way, happy times, check this out. What do you see? Look at that numerator. What is y squared plus x squared? Oh, y squared plus x squared is r squared. Hey, wait a minute. What does that give me? 1. This is my first Pythagorean identity. If you square the sine of any angle and you square the cosine of that same angle, you will always get the number 1. So here's kind of how we play that game frequently. Given, and this is kind of what's going to happen on your next test, I'm going to do something like this. Given that, say, something like that the sine of theta is 2/5. What's the cosine of theta? Now, here's the question. Could you, from our last unit, draw a picture of the sine of theta? Could you do that from our last unit? Where would it be? What quadrants could this be in? First? It says the sign is positive. Could be in 1 or 2. Where would the 2 go? The 2 would go opposite, wouldn't it? Where would the 5 go? Hypotenuse. Could we do Pythagorean Theorem and go get it? Yes, but check out what we're going to do. We're going to start with this idea right here. We're going to go sine squared plus cosine squared is 1. So can you guys tell me what is sine squared according to this relationship right here? If the sine is 2/5, what's sine squared? 4/25. Plus the cosine squared is 1. Oh, by the way, isn't 1 25/25? So I could subtract this 4/25 from both sides and get 21/25. So can you tell me then what the cosine itself is? I wanted to know the cosine, not the cosine squared. What would we have to do? How do we get this cosine squared down to just a plain old cosine? Square root. And what is the square root of this? Would be plus or minus root 21 over 5. Why does it make sense that it's a plus or minus? There was 2 triangles, one in the first and one in the second. That matches. Now, do you notice, did we get the same answer or we would have gotten the other way? You guys see that? Did we get the same answers? But what did we not have to make? I never made a triangle even once. This is a purely algebraic approach, but it totally agrees with what we did before. Okay, so you guys try this one right here. I'm going to make yours really nice and easy. I'm going to say, given that the cosine of theta, I'm going to be nice to you, is negative 3/5. I want to know what is the sine of theta, but I want to see if you will do that without drawing a triangle. Just use the Pythagorean identity. Okay, so please write down the formula we're using, because is this a formula? It's just a simple formula, like the quadratic equation or something like that. What are we going to replace this cosine squared with right here? What are we going to put right there? 9/25, yes. I'm going to leave this alone. So what should we do in an algebra situation? What should we do next? If I want to get this by itself, don't I get rid of the 9? How do I get rid of that 9/25? Minus it. What are we going to get? I was being nice. What do you get? 16/25. Hey, why am I saying I was being so nice? Is because that would make the sign itself what? Plus or minus. Why plus or minus? 2 triangles. I also took the square root of both sides, which always tells me anytime you square root both sides, you get a plus or minus from algebra. What's the answer, everybody? 4/5. So on your next test, what I'm going to say is I'm going to say, hey, go find this information without a triangle. Did I need a triangle? Oh, by the way, sometimes they'll say, oh, hey, do this, blah, blah, blah. Oh, by the way, know that the tangent itself is positive. Well, if you said that, could I narrow down which specific one it would be? Because you would know that the cosine is negative in quadrants 2 and 3. So this would have been a 2, and we would have known that it was this guy. Do you follow me? In your homework, they're going to do that. But I told you that there's actually not one Pythagorean identity, there's 3 of them. So here's the first one. Is this one pretty easy to memorize? Can you guys do that one? Sine squared plus cosine squared is 1. Okay, so here comes the other 2. So I was pretty adamant about not memorizing more than I had to all the way through school. So I still to this day do the same thing. I memorize that one. And when I need the other ones, I do the same thing every time. What would happen if I divided every single one of these things by the same? Can I do that? Can I divide every single piece by the same thing? So watch. I'm going to divide every single piece by a cosine squared. Now, again, I hope you guys are aware of what some of these extra little identities are, but what happened right here? That's the number 1, isn't it? What is 1 over a cosine? Wasn't 1 over the cosine, the reciprocal of the cosine, wasn't that the secant? So this is a secant squared, and this may be the least comfortable, but I know we did it a bunch. What is a sine over a cosine? It's a tangent. So here's my second Pythagorean identity, and almost identical. What could I do instead of dividing every single one by a cosine? What else could I maybe do instead of dividing everybody by a cosine squared? What else could I divide by? A sine, and if I did, I'd get a 1 plus a cotangent is a cosecant. So these are the 3 Pythagorean identities. So in the homework that you're going to get, they're going to do those things. Those are the 3 things. So as I say that, you have to be aware that there's going to be a couple little tweaks that they're going to do occasionally. So just be aware. Can you guys help me restructure this equation a little bit different? Can you move it around so it says the same thing, but it may look differently? Like, as in, what is the cosine squared itself equal to? I like it. You said negative sine squared plus 1? Yeah, I like it. But I'm going to write it backwards. Is that the same thing? If I move this sign to the other side, would that change the identity at all? Can you guys give me another one? What's the sine squared? Okay. Could I play the same game with these guys right here, moving them around a little teeny bit if I wanted to? Okay, so I'm not going to right now. Just be aware of it. So here's what's going to happen in your homework today. So now that I've laid the ground rules, let's do a couple of examples, and then I'm going to be out. So this word right here, simplify, is going to be potentially a little bit, well, unsatisfying to you, because they're going to have a lot of problems like the following, where you look at it and you're going to be kind of irritated because it's a little bit too easy. And I mean that when I say that. So my first example is right here. Let's try to simplify this. So let's go back to our cofunction identities. Can you guys look back and tell me what was this the same as? Go back to the very first thing we wrote down today. What is the sine of pi over 2 minus y? That's the cosine. You got it. That is a cosine of y. But guys, what is a secant? Isn't a secant 1 over the cosine? Isn't it? Oh, a secant, we just, so if that's true, what is this thing simplified? What is 1 over cosine times cosine? That was the answer. There's a bunch of problems that you're going to get today, and if you go through the work, everything's going to cancel out, and it's going to have this very, very small answer. Well, guess why? Look at the directions. It just says, hey, let's simplify. Here's the second one. Number 2. What is 1 minus the cosine squared over the sine? Now, does that look a little bit complicated like an equation or an expression? That looks kind of nasty, doesn't it? But let's look right up here. What did we say right up here was 1 minus the cosine squared? The 1 minus the cosine squared was sine squared. So guys, what would the sine squared divided by the sine be? Sine. So is this right here that I put up, is that easier to look at than that? Oh, so that my directions again are to simplify. Okay, your turn. I want you guys to take the cosine of y times the secant of pi over 2 minus y. Isn't that a cosecant, everybody? What is a cosecant, by the way? It's the reciprocal of the sine. So could anybody tell me what happens if you take a cosine over a sine? What is a cosine? I mean, we know what a sine over a cosine is, don't we? What's sine over cosine? Tangent. So what is cosine over sine? Cotangent. Oh, this is just a cotangent. So if somebody asks you this nasty question, you're like, I don't want to. I'm going to answer that one instead. Isn't that easier? That's much nicer. Okay, getting almost done. I got 2 more to go, and then I'm going to give you guys a little bit of time to practice some of these ideas and just play with them. It's not comfortable, I know, but it is what it is. Okay, these are amongst the hardest problems, I will have to say, as you get into these. Every year, students get a couple of problems like this, and they get really super uncomfortable because when somebody says simplify, when do you know you're done simplifying? You guys ever tried to clean your room and say, hey, mom, you said when my room was done, I could go do something with my buddies? And you think your room is good, and your mother says, no bueno, right? Not going to happen. Like, darn it, I thought I was good. You know, at least there's no like spilled Coke cans on the floor. I did something. I got it better. But see, the hard part about these is sometimes it's hard to know when you're done. And I will admit that this is a little bit tricky. So when I look at this, do I have 2 fractions? I certainly do. So what has to happen if I want to combine 2 fractions together? What do I need? I need a common denominator, and I certainly don't have that. So the first thing that I would coax you to do is, if you can turn everything into sines and cosines, that's a good move. And this problem is not quite there. See, that's sines and cosines, but what is a cotangent? We just talked about that. The cotangent is a cosine over a sine. So the first thing I did is I turned them, everybody is nothing but sines and cosines, okay? Now, as such, what did you learn back in elementary school happens if you ever divide something by a fraction? This is a harder problem. What do you do when you divide by a fraction, everybody? You flip, and then you multiply, right? So if I took this thing and I flipped it over and multiplied, it would turn it into a sine cubed over cosine squared. So guys, you tell me, have I achieved anything that is actually helpful so far? Is there anything that I have done that is helpful yet? I have a common denominator. Now, by the way, so if I put them together as my common denominator, and my whole goal was to make this problem easier, I don't think anybody in the room is going to pay big money to say, oh yeah, that was way easier. Was it? I don't think so. But check this one out. Factor a sine out of the top. Can I do that? Can I pull a sine out of both of them? These are those problems that math teachers do, and if you've never seen them before, I understand why they're like, why would you think to do that? Well, because I've played the game before. Go back to your Pythagorean identity, everybody. Can you tell me what this is? Go back, look at it. You know that sine squared plus cosine squared is 1. Can you guys tell me what sine squared minus 1 is? Think through it. What is sine squared? Take away 1. Can you move this around a little bit and tell me what that piece is? Can you see it? What is it? Almost. Very close. What is sine squared minus 1? If I wanted to get this by itself, what do I have to do to that? Don't I have to subtract it to the other side? What does that make it then, everybody? Isn't that negative? So here's the deal. This is sine x, this is negative cosine squared, this is cosine squared. What's left, everybody? What happens to those cosines? They're going to cancel, aren't they? What's left? The sine, and what else? A minus. That minus is still there. This entire crazy thing became negative sine x. Now, again, if my goal is to simplify, what do you guys like better? That dumb thing right there or negative sine x? Isn't that a lot easier? That's, again, this is a strange little bit of a goal. So I want to see if you guys can play with this one yourself, because this is what you're going to be asked to do in a moment. I want you guys to take a secant of x divided by a sine, and I want you to subtract, or actually I want you to, subtract sine over cosine. Now again, the first thing is turn everything into sines and cosines, try to make a common denominator, and let's see what we can figure out, okay? I'm going to give you a minute to see what you can come up with. And this is my last one for a good long one. And I'm going to give you guys 20-something odd minutes to work. Remember, secant is 1 over cosine, isn't it? So secant on top makes it a cosine on the bottom. I'm going to pause a minute. See if you, what would you need to do to make a common denominator? Okay, who can help me out? What does this fraction over here need so that it has the same denominator as this one over here? What does it not have that this one does? This denominator has a sine and a cosine. This one just has a cosine. What does it need? It needs a sine. So how am I going to give it a sine? Because I put 1 in the bottom, and what do I also need to do to keep it fair? Put 1 on top, right? Do I have a common denominator now? Yes, I do. So let's see if you guys can play the game the rest of the way out, because that should look familiar, because we talked about that not too long ago. Does this look familiar? What is 1 minus the sine squared? What is 1 minus sine squared, everybody? Doesn't it say 1 minus sine squared is cosine squared? Ooh. Is there anything you guys could do to clean that up a little bit more? You notice anything? What can cancel now? A cosine on top with a cosine on the bottom. So if those two cancel, I'm down to here. Still have that sine, but what's cosine over sine? That's cotangent. Done. So when you look at this, this is nasty, but that's not so bad. And so this is again called the topic called analytic trigonometry. So right now, what I want you guys to do for about the next 20 minutes or so, I want you to take out your books. Now I actually posted it, so open up your Chromebooks and I'll kind of show you how we're going to do this. We're going to, I'm going to go ahead and bring this over to this screen. Should be fine. And let's do a new share to the computer. So what we're going to do is we're going to go into our Chromebooks. And what I did for you is I actually uploaded your textbook. It's right here, Chapter 5 text. And I also put the Chapter 5 homework right here. So your text is right here. You can open that up and get it. And this is your list. So what you're going to work on is these two assignments right here. And I know that that sounds like a lot, and it only sounds like a lot because it is. But what I have is I've got a series of 4 assignments for the week, which are these 4 right here. These 4 right here are going to carry us the entire week. So these 2 are for today. These 2 are tomorrow. And then Wednesday is going to bleed over and be picking up those pieces that we need to do. So I kept them as separate things, but I'd like you to go to 5.1. The reason I did it as A and B is because normally we have 2 different days to do that, but with blocks I have to do 2 to 1 kind of stuff. But I am giving you an extra day this blank because on Wednesday that's where we're going to be. We're going to be kind of cleaning up some of these ideas. So anyway, why don't you guys start up on here, go through 1 through 7 and do those odd problems, and I will walk around and help you. Some of these are going to be pretty quick. Some of them take a little bit more time. So that's where we're going to stop at least for now. All right. So as far as the video goes, I was going to do a little teeny bit more, but I just don't think people can handle it right now. So we're just going to go ahead and stop the video, and I'll just put the next part on the next day. All right. See you.